everyone. This is Alex, and welcome to our mathlete.org YouTube channel. We'll be talking about target problem 6 from the October 2020 high school test 12101. Okay, compute the sum of the digits of the binary representation of 1025 to the third minus 2. This kind of looks like a one-liner, if I do say so myself, right? But is it as simple as it looks? Well, let's see. Okay, binary representation. First of all, what do we know about binary representations? Well, they're base 2, so they consist only of zeros and ones, right? Those are the only possible digits in base 2. And each digit corresponds to a place value that's a power of 2. So kind of like, for the sake of example, to write some place values here from 2 cubed to 0. So if we wanted to represent 2 cubed plus 2 squared plus 2 to the 0, which is the number 13 in base 10, we would write it as 1, 1, 0, 1 in base 2. That's 13 in binary, right? So just for the sake of familiarity there. So what we really want to do is count the ones in this binary representation, right? Because all of the other digits are zeros. We just want the sum of the digits, number ones, right? All right, so how do we convert this large number, like 1025 cubed minus 2, into binary? Well, how do we usually convert numbers into binary? Well, perhaps we can try just sort of scouting for the largest powers of 2 first, that are less than or equal to our number at every step, and then subtracting them from the number repeatedly until we reach 0. That seems kind of ineffective, though, because where do we even start, right? Besides, what we need is an exact representation, and we simply don't have the time to go through and exhaust all the possible powers of 2. So, let's see. Let's think about the powers of 2 a bit longer and a bit harder. Is there anything special about the choice of number in this problem? Why is the problem specifically asking about 1025? What's special about 1025? Well, we could start with the fact that 1024 is a power of 2, right? So 1025 is actually 1024 plus 1. And that's actually 2 to the 10th power plus 1. So we can write 1025 is 2 to the 10 plus 1, and then you expand out 2 to the 10 plus 1 cubed minus 2. You can apply binomial theorem here. That'll give you, well, remember that x plus y cubed is x cubed plus 3x squared plus 3xy squared plus y cubed, right? Therefore, if we let x equals 2 to the 10 and y equals 1, then we'll get the 2 to the 10 plus 1 cubed is equal to 2 to the 10 cubed, that's 2 to the 30th, plus 3 times 2 to the 10 squared, that's 2 to the 20th, times 1, plus 3x, 3 times 2 to the 10, the 1 is just there, so y squared, that's 1, and then you have y cubed equals 1, right? So you end up with 2 to the 30th plus 3 times 2 to the 20th plus 3 times 2 to the 10th plus 1. Okay, so far so good. Only one issue, though, which is that the concept of 3 doesn't really exist in binary, and if it did, it'd have to be 11, not a single digit 3, right? So how do we get around this? Well, if we wanted to write, let's start with 3 times 2 to the 20th. We'll start with that as the sum of distinct powers of 2. Sum of distinct powers of 2. Well, it's also 2 times 2 to the 20th plus 2 to the 20th. That's going to be 2 to the 21st plus 2 to the 20th, right? And same thing for 3 times 2 to the 10. Same thing. That's going to be 2 times 2 to the 10. That's 2 to the 11. 2 to the 11 plus 2 to the 10th. Okay, great. So now we have our representation as the sum of distinct powers of 2, and that's going to be 2 to the 30th plus 2 to the 21st plus 2 to the 20th plus 2 to the 11 plus 2 to the 10 plus 1, right? So really now we have our binary representation of 1025 cubed, but that's not what the problem is asking for. It's asking for 1025 cubed minus 2. So that's going to be 1025 cubed. We keep all the powers of 2, right? We just have all these guys just carry over, but then we have a minus 1 instead of a plus 1. So that's going to be our 1025 cubed minus 2. So what we have to effectively do now is kind of like a reverse binary carryover. So now we have to think about kind of what happens when we subtract 1 in, like, say, base 10. Well, when you subtract 1 from a number like 100 in base 10, that's going to be 99, right? And 29,000 minus 1, for example, is 28,999. So we notice that all of the digits that used to be zeros are now 9s, because it's kind of like, you know, it's like borrowing from the 9th place and just adding it to all the zeros, right? So if we want to apply that same logic here, well, let's just ignore everything else in this part for now. Let's just look at the 2 to the 10 minus 1. 2 to the 10 is just 1 with 10 zeros after it. And if we subtracted 1 from that, we would end up with, well, 9 ones. Right. So all we have to do now is represent, or 10 ones actually, because all we have to do now is represent this in binary. So, well, the everything else can stay the same, right? You have a 1 in the 30th place value, the 2 to the 30th place value. You have a 1 in the 2 to the 21st. You have a 1 in the 2 to the 20th. You have a 1 in the 2 to the 11th. And now you have 10 more ones. So in total, we have 14 ones, which means our digit sum is 14. And we're done because all the rest of the digits are going to be zeros. So that's our final answer, and we're done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.